Hey everybody, I'm going to talk about hydroboration-oxidation in this video. And first, before we talk about that, I kind of want to go through a little bit of an overview of the various hydration reactions that we know of so far. So far we started off with sulfuric acid and water in a way of putting water across an alkene pi bond. So in that one, we do need to make sure that we're watching for rearrangements, because we are going through a carbocation intermediate. So when we use this reagent or this starting material, we're going to end up seeing this product where we're putting the OH on the more substituted, more stable carbocation that forms. And then we said, well, if you don't want that carbocation rearrangement and you just want to have your OH on the most substituted side of an alkene, then you could go ahead and use your oxymercuration demercuration reaction. And then that's going to cut down on all of your rearrangements and get you to your OH that way. But we have not yet talked about a situation that will allow us to get to the least substituted alcohol, which would certainly be useful in a few cases that we've seen so far. So if you want to have an alcohol here and then you want to just like change that into a leaving group, then you've got functionality at this carbon rather than this carbon or that carbon. So it's just going to open up what we have in terms of options. So that's where hydroboration-oxidation comes in. So these are the reaction conditions for hydroboration-oxidation. We are going to talk about this mechanism because it looks like there's kind of a lot going on here, but we'll break it down and make it a little bit more reasonable. So for hydroboration-oxidation, again, this is another hydration reaction. So we're adding water across an alkene. So we're still adding an OH and an H, except in this case, we're adding that OH to the least substituted side here, okay? And then we also see that occur in a syn fashion, so the H and the OH are going to be syn to each other in this particular reaction. So if we draw out the product here of the one that I have drawn, we're looking at something like this, where we've got the H on the more substituted side, the OH on the less substituted side, and these are syn to each other. So they are both on dashes. And then this is also going to form the enantiomer as well, because this is a chiral molecule. Okay, so for the mechanism here, okay, there's really one part of the mechanism that I want you to know. So I'm going to make sure that I label those very clearly. So the hydroboration, this is the part that I do want you to know. Mostly because this is the part where we set the regiochemistry and the stereochemistry, and then the oxidation step, which is that second step, with the hydrogen peroxide, the sodium hydroxide, the water. That's going to be your oxidation step where you're getting rid of your boron. So for the hydroboration, so we have our alkene and we've got BH3. Okay, so I have a couple different ways that I could line this up. So we're just adding a boron, BH2, and H across the pi bond, okay? So when we're looking at boron, the thing we want to keep in mind here is that boron has 3 valence electrons, right? It has 3 things around it. It's now neutral. It's also sp2, so there is an empty p orbital, just like there would be on a carbocation, okay? So the carbocation geometry is very similar to what we see in boron. So what we're going to do here is we're actually going to have our pi bond go and make a bond to the boron, but instead of forming a carbocation, that hydride, basically an H minus, is going to leave from the boron and go and add on to the carbon of the alkene. So there's basically 2 ways that I could do this. So I could have it the way that I've already drawn it, or like this. Okay, so basically what I have here is this is adding boron to least substituted side. And this is adding the boron to the most substituted side. Okay, so looking at that, it's kind of clear which one is a more comfortable fit, in that if we have the boron where there's less substituents, we have a lot less that we're running into like we would do over here. Okay, so this is definitely a bit of an issue. And that's why we see that regiochemistry of the preferred least substituted side. Okay, so we're really looking at this is a much more comfortable fit. And this is way too crowded. Okay, so once we do our final hydroboration step, I'm just going to draw a line down here. So that's going to get us to this intermediate. So, and this is the situation where essentially I've got my boron and my H coming in. They're going to add to the same side of the alkene. Okay, so this is our syn addition. Because I've got my boron and my H, they both have to come in either from the top of that alkene or from the bottom of that alkene. So they are both going to be on the same kind of stereochemistry. So I'm going to go ahead and put them on a dash. Which makes this methyl group on a wedge. Okay, so we've got a syn addition of the boron and the H. So this can keep on reacting until these other two H's are also used up. So we're looking at two more equivalents of our starting material. Okay, so that we end up getting, I'm not gonna draw the whole thing out because it'll be horrendous. But we're basically going to be looking at R and R, so that we have a trialkyl borane where all of this is R. Okay, so I want you to know that you at least get to here, because that's all the important stuff in terms of stereochemistry and all that. So the whole oxidation part is literally just replacing the boron here with an OH is all it is. Okay, so the oxidation step, this is the part you don't need to know this. So what I do want you to know is that this whole big thing with hydrogen peroxide, sodium hydroxide, and water turns into this. And the enantiomer, which I should have put up here. Okay, so all I want you to know is that you're basically just replacing that bromine, that boron, with an oxygen to get your alcohol product. Okay, so for the For those of you that really like to see the mechanism, this is what that mechanism looks like though. So we first start off with hydrogen peroxide. It's got a pK of about 12. And we've got sodium hydroxide around. So we've got OH minus. So our first step is just an acid-base reaction. Oops. Would help if I actually deprotonated something. Okay, plus water, pK of water is about 16. So we have a reaction where we're definitely favoring the product side, which is what we want. So then we can go ahead and bring in our trialkyl borane. Okay, so I've got my trialkyl borane, I've got my deprotonated peroxide. So we can go ahead and use that peroxide to attack our boron. So boron can definitely have a full octet. It is negatively charged when it is in that state, but it's definitely possible to do. Okay, especially when you're considering here that the boron has that empty p orbital, so it's basically an electrophile. Okay. Alrighty, so we attack. So we've got now this intermediate. Oof, I'm not giving myself much space here. Actually. Okay, so now my boron is negatively charged because I've got 3 valence electrons, but it has 4 around it right now. So this next step, it's a little bit weird, but it helps to think about what boron needs to do in order to become neutral again. And it really just needs to like push electrons away from it and give those electrons to something else. So the way that it's going to do that is we're actually going to see an alkyl shift. So very similar to like a carbocation rearrangement. So we're doing an alkyl shift onto this oxygen because as we've seen before, that OO single bond, very, very weak bond. So if we push onto that oxygen, this bond is going to get broken and we're actually going to see OH minus work as a leaving group here. Okay. There are a few very specific circumstances that we're going to see hydroxide as a leaving group. This is one of those circumstances. Oftentimes you're going to see it only when you are already in a basic solution. So you already have a whole bunch of hydroxide around, which makes it a little bit easier to generate more. This one is also particularly favorable because that OO bond wants to break anyways. So this movement kind of just forces that off. Okay, so then we end up with our boron, still has a couple R groups on it. We've got an O. And then we have this product. So I just took this whole piece and I shifted that over to that oxygen. Okay, so none of the stereochemistry changed because essentially we're thinking about this as our nucleophile. So this stereochemistry is not going to change, just like in the tosylate formation, it just stays the same. Okay, so then this is going to repeat a few times. Oops. Need that. So this is going to repeat all from the first to here. Okay, 2 times. And that's going to get us to a trialkoxyborane. Okay, so once we're at this trialkoxyborane, it is pretty much done all that it can. So we basically just made that 2 more times, right? So that we have OR for all of them. And then we're gonna have our hydroxide come in. And again, that boron is still fairly electrophilic because of that empty p orbital. So we're gonna go attack that boron with our hydroxide. So that's a nucleophilic attack right there. Okay, to get to this intermediate where our boron is again negatively charged. So because that boron is negatively charged, again, we're looking for a way to kind of push electrons off. So we're just going to go ahead and pop that off as a leaving group. And then that's going to get me to B, OR, OH, OR. Okay, then I have very close to my product at this point. So we're just going to keep on repeating this. So we can protonate this. Okay, and this is going to repeat until we get to, until we have our boronic acid. And then you're going to end up with 3 of these. Okay, so that's really what's going on here. Again, you don't really need to think about the oxidation part of the mechanism. The important part of it is I want you to be able to know what's going on here. Okay, this is the important bit. So as long as you can think about this and get to here, that's all I care about. But if you really want to know what the mechanism looks like, it's right here. So as always, let me know if you have any questions, and I will see you all later.